All right, I think we're about ready to begin. First of all, I want to thank everybody for joining us tonight. I'm quite excited. I've had a lot of PHSNE in the last couple of weeks. We had a huge Photographica show last Saturday. We had over 70 dealers come in selling antique cameras and you know, those cameras that were used not too many years ago that had become collector's items. So it was great to see. We had over 400 people show up, and it was a huge success. So I'm still riding the success of that. I also just want to remind people, you know, we're always looking for volunteers, especially with our journal and other things that we do. So if you do have some time and want to help us out on this great organization, please do so. And we also will gladly accept donations. We run on a volunteer basis, but it is expensive, all the things that we have going on. So if you want to make a donation and especially join PHSNE, I would encourage you to to look up our website, a brand new website. It's fantastic. Thanks to Rick Lent, who put that together for us. So with that, I'm going to turn it over to Dana, who's going to give us some instructions. And with that, Dana, you want to take it up?
Thanks, John. Hi, I'm Dana G. I'm the program coordinator for PHSNE. Just before we introduce Phil today, I just wanted to do a few little housekeeping things. Please stay muted throughout the entire presentation. And as we go along, if you have questions, please type them into the chat, which you'll find at the bottom of your screen. And I will monitor those. If there's something that you would like to have Phil answered during the presentation, just put a little asterisk or something, or, you know, I'll try and stop during the presentation at good points to ask Phil those questions. And then the rest of the questions I will relay to him at the end. And after that, if people still want to have brief, quick questions, they can unmute themselves. But until then, please stay muted. If you go up to the top of your screen on the right for view, speaker view is best for this presentation. And then at the end, when we're just chatting and hanging out, gallery view is better, and you can switch back to that. But I would stay in speaker view. And if you have technical difficulties, post them in the chat. We'll do our best to answer. And when you use chat, please use the default everyone setting so that we can all see the chat questions. At this point, I'm going to turn it over to John, who will introduce our speaker.
Thank you, Dana. Yeah, a little bit different this month with me actually introducing the speaker. And the reason we did that, I was talking to Dana about how we actually got Phil to contribute an article to our journal. You know, it's funny how things work out. One of my part-time jobs in the summer is a lecturer on a cruise ship. And I was doing this a few years ago, and one of my responsibilities, I take it very seriously, is to attend a happy hour, open bar happy hour with the guests every evening before dinner. And so I was doing that. It's like the first or second day, and these people were raving about this guy and his lovely wife, who they had met earlier in the day, who designed a camera that uses a satellite. So of course my ears perk right up as soon as I hear camera. We broke from that conversation, and I'm sitting down at dinner with some completely different people. And once you know, the topic of the conversation from these people was about this guy that they met earlier in the day, who designed a spy satellite camera. And finally, the next morning at breakfast, again, totally different people, they said they were talking about Phil Pressel. And I'm saying, okay, that's it. I got to meet this guy. And I sought him out, and we talked. And he started telling me a fascinating story about his work and his life. And the things that he did. Now, I'm not a big camera person, but I do know how easy it is to take a blurred picture. And when he was explaining to me the challenges of taking a clear picture from a satellite moving 17,000 miles an hour on the Earth that's rotating at 1,000 miles an hour. I was just totally blown away. So I said, we have to get this guy in for a speaker, and Dana agreed and invited him in. So with that, I'm going to turn it over to Phil. Let me just say, though, he grew up in Belgium for the first couple of years of his life. He got caught up in the Nazi invasion of Belgium, and his family whisked him off to France, where they were actually hidden out by a Catholic family in France. His father was fluent in like 8 different languages, and with those skills, he got a job as a translator for the United Nations, and ended up in New York. And it was there that Phil learned English, went on to NYU to get a degree in mechanical engineering, and from there went on to Elmer Perkins. So that's all. That's the I was going to tell you. I'm going to turn it over to Phil, and from there he can tell you the rest. Phil, why don't you take it away?
Okay, thank you very much, John. Appreciate it. I'm so happy to have met you on that cruise. So, okay. Can you see my presentation now? Let me share. Can you see it? All right. Can you see me? Ben, that means yes? Okay, great. So the name of the program was Hexagon KH, stands for keyhole, and that's a code word by the CIA for overhead reconnaissance. And this happens to be the best reconnaissance or spy satellite ever made by the United States using film. Basically, the satellite orbited the Earth. The Earth rotates from west to east. This is the satellite that rotated in a polar orbit. That means north to south around the globe, therefore allowing the cameras to take pictures of the entire landmass of the Earth. The left picture shows it taking photographs. The right-hand picture shows one of the 4 re-entry vehicles that carried film back to Earth, was ejected every few weeks or every few months, depending on the mission. It could take very wide angle pictures, such as this one of the San Diego area. It actually could take much, much wider area photographs of, for example, Syria or Iraq. Now here's a picture from the White House. The gentleman in the dark jacket leaning over is former President George Bush when he was director of the CIA, and the gentleman on the right leaning over, and they're both examining a picture generated by the Hexagon satellite. And okay, this is a typical picture that we took. This one happens to be of the San Diego Naval Base. All of the pictures that I'm going to show you are of medium resolution. I will talk about resolution later, but the really good close-up pictures I'm still not allowed to show you because they're still classified. So this will be the type of pictures you will see. Here's a picture of Pyongyang, North Korea. Again, same kind of resolution. Here is an isometric color drawing of the entire satellite. You can see the solar panels at the rear. The next compartment has electronics. The next compartment with the white circle are the 2 rolls of film. There were 2 cameras on board, and each one had their own reels of supply reel of film. I will show you more details about that. Then the 2 black cylinders forward of the supply reels are the two cameras. The two cameras, which I will describe in detail, were aimed, one was aimed forward by 10 degrees, the other one was aimed backwards to the rear by 10 degrees, creating a 20-degree stereo angle. So we were able to take pictures and determine the height of buildings, missiles, etc. And the 4 reentry vehicles are at the front. The first one that was returned was the one on the extreme left, and the second, third, and fourth. Okay, the challenge by the CIA was to improve the resolution from worse than 6 feet, from 100 miles up in space, to about approximately 2 to 3 feet. Corona was the first spy satellite. It did not have very good resolution. You could only see objects perhaps the size of a car or a truck. We were tasked to be able to see things that are like a small table, 2 feet square. And we did that. And I'm not allowed to tell you, but we did much better. We also were tasked to produce global mapping and local imagery in stereo, meaning if we flew over a Russian missile base, an air base, a tank base, a submarine base, etc., we could close up on it and see it up close. Some of the difficulties that we had were several that John mentioned, and that is, first of all, the satellite weighed a total of 30,000 pounds. And the satellite, the rocket that was able to launch it from Vandenberg Air Force Base in California was the Titan. That there was first a Titan 3D and eventually the Titan 34D. So one of the problems was, after all the vibration and shocks, to maintain the alignment of the lenses and the mirrors and the focus after launch loads and during global orbital temperature changes. Now, we were able to maintain the temperature change of the satellite camera and film system to plus or minus 23 degrees Fahrenheit passively, meaning we had no heaters, no cryo, no coolers. We did it all passively, meaning the colors of various objects, the cameras, the electronic boxes, the containers that held the film, for example, were either very shiny to reflect heat away or very dark to absorb heat. The other problem that John Felix did mention was, how do you solve a blurry pictures? You're taking pictures of a racehorse going in front of you. It's going to be blurry. So here you have an Earth that moves, that rotates. You have a satellite that rotates, as John said, at 17,000 miles an hour. You have 2 cameras that are, during photography, constantly rotating. And you have film rotating and passing by the focal plane at extremely high speeds, depending on the altitude of the orbit. So these were major challenges. Well, we flew 19 Hexagon missions. The first one was June 15th, 1971, until April of 1986. These missions all helped keep the peace in the world by determining exactly what our enemies were doing. So it provided the technical means permitting President Nixon at that time to sign the SALT Treaty. And then President Reagan was able to say, trust, but verify. And how did they verify? Using the satellite and its cameras. And this was, at the time, and I believe it still is, first of all, there were no failures. It was the most complicated satellite ever put up in orbit. And the reason for that is we had tremendous amount of moving parts. I'll describe some of those parts as we go along. Other requirements were we had 4 capsules of film that we after photography, when they filled up, they re-entered the atmosphere just like the astronauts did in their re-entry vehicles. And they were caught at around 50,000 feet by a KC-130 plane over the Pacific, brought to Hickam Air Force Base. The film was immediately unpacked and sent to us at Perkinamer and to the CIA for examination. We had very, very high reliability. We've wasted very little film. And the whole program was under extreme security. It was top secret. It was beyond top secret. The mushroom patch that I show here means at the beginning of the program, when we won it in 1966, we had to hire hundreds and hundreds of people to work as engineers, inspectors, etc. They all had to have a security clearance. We could not tell them what they were going to work at. So they took a chance on getting a clearance, not knowing what they were going to work at. And we took a chance on them whether they would pass the clearance. And it usually took 4 months to close to a year to get clearances. So what did we do with all these hirees? Well, we put them in a huge room the size of a gymnasium with lots and lots of desks, and a few with certain talents we put to work with certain assignments without telling them what it was for. And everybody else, we fed them. They could read books, newspapers, and we called that area the tank. And we also called it the mushroom patch. The reason for the called mushroom patch is because we kept them in the dark and fed them a lot of crap. We did not have technologies like we do today in the 60s and 70s. We had no CAD, we had no microprocessors, no LEDs, CCDs, very limited computer use, no pocket calculators, and no printers. What did I use for most of my career? I used a slide rule. Technology that we did develop and invent were optical encoders, which we used to commutate brushless DC motors. We invented DC motors because we could not tolerate the electromagnetic interference that brushes would create. And they also created dust. We could not tolerate any dust. All materials had to be free of being outcast, meaning sublimation, evaporation of contents of any material that outcast would deposit on the lenses and bearings, and that could not be tolerated. We also used light pipes to transmit data. We invented very complicated film handling mechanisms for the simultaneous motion of film in a linear and rotational movement. We invented closed loop phase lock servos, and we used very high resolution Kodak film, both black and white and in color. I will talk about film. Here's my slide rule. Okay, this is a side view. This is, you can see me on the right pointing to the area of the actual, this is an actual satellite, which is on display at the United States Air Force Museum in Dayton, Ohio, at the Wright-Patterson Museum. I'm pointing to the areas where the film was stored. The 2 cameras are just to the left in the middle of the screen. You can see one black circle, which belongs to the camera that is looking forward by 10 degrees. Just to the left of it, you can see the camera is aimed 10 degrees aft, and those are the 2 cameras. The 4th and 3rd re-entry vehicles that return film are shown to the left. there is a window right above in the black part of the vehicle. I'll show you the window on the other side in a minute. I'll tell you why it was there. Right in front of me are two circular pressure vessels. These contained dry nitrogen gas held at 3,000 pounds per square inch and then pressurized down to 1.5 pounds per square inch. And the reason for that is very important. The emulsion on the film in space could evaporate as well as lose its humidity. So the entire supply container and the entire film path leading from the supply through the cameras to the reentry vehicles was pressurized with 1.5 pounds per square inch of nitrogen. And that was the supply source. Okay, this is also an important view graph. It shows the two cameras, again, aimed at the two stereo angles. Each camera was 6 feet long, weighed 600 pounds. They were held at the proper angle in a huge aluminum frame that also carried a whole bunch of electronic boxes. The two boxes that you see on top of the frame, one to the upper left, one to the lower right, those are called loopers, and I will explain their use shortly. Okay. I just showed this picture, excuse me. All right, this is the other side of the vehicle. Again, you can see the two cameras aimed slightly, one forward, one aft. And you can see above the right-hand camera an open door. And through that open door, there was a camera, which I will show you next. This camera I worked on, and it was called a Star Tracker. And it was designed and used only on the last 2 missions of the program because it contained very, very sophisticated CCDs, LEDs, coolers. This was a Star Tracker, which set the stage for the Hubble Space Telescope's fine guidance systems. Those fine guidance systems were so accurate that they could aim the Hubble Space Telescope so accurately that if you aimed the camera like what you're seeing now from New York City with a rifle, you could hit a tennis ball in San Francisco. Incredibly accurate. Okay, here is on the pad. The Hexagon was on the top portion of this Titan 3D solid fuel rockets bolted on the side of the main rocket. Okay, here's a picture again, not great resolution, of the Leningrad shipyard. Here's a schematic. So from the right, you see the 2 large circular containers. They were about 6 feet in diameter, one behind the other, containing film. There were each reel of film for each of the 2 cameras carried, first of all, the film at the beginning of the program from Kodak was 6.5 inches wide, about 2/1000 of an inch thick, and each camera carried at the beginning 10 miles of film. So the 2 cameras carried 20 miles of film, several miles of black and white, followed by several miles of color, etc., on and off, spliced together. As Kodak developed better film, they were able to improve the resolution and able to reduce the thickness of the film from 2/1000 of an inch to 1.2 thousandths of an inch. Thereby, we were able to increase the amount of film that each mission carried And each camera carried 30 miles of film, total of 60 miles. The film weighed thousands of, each container, supply container carried approximately 2,500 pounds of film. You can see the film coming out of the supply circle through a chute. The chute brought it to the looper, which I will explain. The looper was a storage container that fed the film to the camera's focal plane. After photography, the film was returned to the looper and shipped all the way through each of the 4 re-entry vehicles to the first one. When the first one was full, it was released. I'll explain more of this as we go along. Here are the 2 cameras. You can see the camera closest to you in the vehicle is aimed at one angle, and the other one you can see is aimed at another angle. They were all tied with many electronic boxes to that frame I showed you before. I forgot to mention before that in that frame, the cameras and all of the large, heavy, rotating devices, such as the cameras, the supply reels, all rotated in opposite direction. The one on the right rotated counterclockwise, the one on the left rotated clockwise. And the reason for that was momentum compensation, because if you had the 2 cameras rotating in the same direction and the 2 supply reels rotating in the same direction, you would create a tremendous unbalance, and the whole vehicle weighed 30,000 pounds, it would wobble all over the place. So everything that rotated was in opposite directions. In this picture towards the right, you can see, look, it's a circular, right above the 2 spherical pressure vessels, you see a lens. It looks like an ellipse, but it's really a circle. And that is the entrance lens to the optical system.
We have a question, Phil.
Yes.
Ben is asking, was there a cover over the cameras during blast off? And how was the cover discharged, if so?
Good question. During launch and during non-photography, during photography, the cameras were both launched and aimed at nadir, which is directly looking down at the earth. During launch and during non-photography times, the cameras were all aimed at zenith, towards the inside of the vehicle. And the prior, right after this vehicle was launched, was put in orbit, there was a cover that covered the inside, the bottom half of the vehicle, and that was ejected, and what remained was a fiberglass, thermal, and optical shield, so that no heat or light, and they were all baffles, could enter the camera. And the cameras were only rotating during photography. I hope that answers the question.
There's one more quick question where Anne asks, were the same cameras used on MOL?
Yes, it was. Well, MOL never really flew. The manned orbiting laboratory was a job that we proposed to use the same cameras, slightly different configuration, which would be launched on the shuttle and manned by astronauts themselves. We proposed it. My last view graph will show that the Hexagon vehicle, all 60 feet long of it and 30,000 pounds, would have fit into the shuttle by 2 inches clearance lengthwise. And we proposed that it would have done is when the camera was out of film, the shuttle would have gone up, retrieved, grabbed the whole vehicle, brought it to Earth, replenish film, replenish gas, fuel, etc. But that program was never approved, and Mole never flew. Okay, so here's the camera. The camera was an f3 60-inch focal length camera. So the aperture, this last lens here, right above the spherical vessels, was 60-inch focal length divided by f3, which means that the clear aperture defined by a knife edge was 20 inches. That last lens, the first lens in the system, was an 8-sphere, and it had a clear aperture of 20 inches. Okay, so the camera 6 feet long, the primary mirror shown on the right, the corrector plate at the bottom was that indeed that 20-inch diameter, 1-inch thick lens. The image came through from the Earth. It hit the diagonal mirror, which was mostly rectangular. It had the sides lopped off. That mirror was at a 45 degrees. It aimed the image to the primary, which then focused it through the field group, which was a set of 4 lenses and an interchangeable filter. That would be 2 lenses that could be rotated 90 degrees, one for color film or rotated the other way for black and white film. All of the glass basically has a very, very low coefficient of expansion, like 0.3 parts per million per degree F per inch, while aluminum has a very, very high coefficient of expansion, like over 12 parts per million, right? So what we wanted to do is we had to compensate as temperature increased or decreased, even a small amount. We had to keep the focal plane, the focal length from the primary to the focal plane. And you can see the focal plane labeled at the top left. Focal plane is a straight line there. And that distance had to remain at 60 inches, and it had to remain there within 2 microns. And a micron is 40 millionths of an inch. The back focal length, meaning the vertex of the last lens, had to be within 1 inch and 2 microns from the actual rollers that define the focal plane. And so the mirrors were all held with a material called Invar. Invar is a stainless steel material with a 36% nickel content, which makes it have a coefficient of expansion of almost the same as the glass. And so all the trusses that hold the glass, the 2 mirrors, were made out of Invar. Then how do you hold, and they held the mirrors laterally. How do you hold the primary mirror axially and keep it in control temperature-wise? Well, they were, at the middle it says Invar metering rods. There were 3 rods, about 3/4 of an inch thick, hollow, made of Invar, that held the truss from behind the primary to a small piece of aluminum, there's a bulkhead at the very far left that held the whole optical system, made out of beryllium. The reason for beryllium is it has the highest strength to weight ratio of any metal. And so the metering rod of Invar is attached to a very short, maybe 2 inches long aluminum rod. So as the temperature increased, the aluminum pulled the primary mirror to the left, and the 5-foot length Invar rod pulled it to the right, and an equal amount based upon the coefficients of expansion of all the materials in series. And we were able to keep the focal length and the alignment perfectly. We used a lot of mechanisms and flexures to hold the mirrors at the central point to minimize bending of any optics. We didn't use this kind of film, which you are all familiar with. We used a number of film. It was called 1414 or SO302, totally different from a photographer's use. And the film, of course, didn't come in this kind of container. It came in, it was a huge container, which I'll show you next soon. 6.5 inches wide, totally different. Here's the container. It was 4 feet wide. The diameter of the film, which is shown in the right side, was approximately 6 feet. So out of the two circles in the middle, the film came out. The whole container was filled with dry nitrogen gas, and there was a latch, a mechanism that closed the door when there was no photography to keep the gas from leaking. This is the whole film path from the right. That's a supply reel going through hundreds of rollers. Each roller, I'll show you each roller. That's a roller. It's about 7 inches long, the size of a finger, hollow, made out of beryllium in order to save weight and torque, inertia. You go back to this. So all the rollers together are the two loopers, which I will explain next. And here I omitted the cameras for clarity. The point right here, that's the focal plane. This area here, can you see the arrow? Point up if you see it. You do, okay. So this is called a twister. This is an invention by one of my colleagues. It enabled us to do what we did. The looper and the twister were key to the whole program. So the film came off, it went to the A or B side camera through the looper. There's a carriage here that went back and forth down to the focal plane in the camera, and then back to the other side of the looper, and then it went to the re-entry vehicles. I'll explain a little more. This is very complicated. I'll do the best I can. Okay, so the important thing, the real key thing, and the heroes of this program to me were the servo electrical engineers, because they were able to, okay, here's the key was to synchronize the rotating image, which was rotating and at speed, with the film position and speed. And the film, the orbit was from 85 miles perigee to about 150 miles apogee. Obviously, the best resolution was at perigee. And at that position, the film went past the focal plane at an incredible speed of 200 inches per second. At apogee, it went about 1/3 of that speed. So they were able to match the speed of the film, which went whoosh, fast, with the image. And they did it perfectly. And the key numbers to do that were V/H. In the first paragraph, I say, V is the velocity of the vehicle above whatever part of the earth it was rotating at, divided by its height above whatever it was photographing. And that was the key thing. We were also able to photograph scan angles. If you look at nadir, plus or minus 60 degrees about nadir, which was a total of 120 degrees scan. Each degree was 1 inch of film. So for 120 degree scan, you had a 10-foot piece of film. So the photo interpreters at the CIA and we had to create our own 10-foot long light tables, one in front of the other, using a stereoscope to see stereo. So you had huge tables. But we could also take photographs plus or minus 10, 20, or 30 degrees at nadir or off axis. And so what I'm going to talk about next is I'm going to make believe we're doing a 120-degree scan because it's much easier for me to explain that. Okay, let me give it a shot. Okay, the film came in from the right side, from the supply. And okay, here we go. It went through the looper. This is a carriage. This is a carriage that moved. When it moved to the left, it drew 120 feet of film into the looper, while feeding film that had already been taking photographs into the platen means into the focal plane area. When the carriage moved back, it sent the film to the reentry vehicles. Okay, let me show you. So the purpose of the looper is to store film, feed it to the twister, and then to the reentry vehicles. The advantage to this, besides that it was able to do, was that the supply reel had 2,000 pounds of film on it. It would have taken a huge motor power to pull it off the supply reel. Meanwhile, here you only had 120 feet of film, and so therefore it could easily pull it and send it to the twister. Okay, the twister. This is the last lens of the camera. And remember, it's going to be rotating. It's going to be rotating. I'm going to use my hands now and show you how this works. The twister consisted of these 4 rollers. Here's a focal plane. And these two are, the rollers rotated, but these two were called D bars. They were stationary bars. They did not rotate. They oscillated. So what happened was there were holes in it that you can see, and the dry nitrogen that I explained earlier goes through the system and it exits through those slots, allowing the film, the Kodak film, to ride on a thin nitrogen film of air, so that there's no friction between the film and the roller. And these rollers and the D bars oscillated back and forth. I'm going to demonstrate that now. If you look at my picture, basically, remember the camera goes around constantly during photography. So, and this is called, those 4 rollers are called a platen twister. So during photography, they are both in sync together. At the end of the 60 degree or the 120 degree scan, the film is stopped for microseconds. Optical light pipes deposit the date, the latitude, the longitude, or whatever airplane base in Russia they were taking. Then the camera continues to rotate while the twister comes back. They meet at -60 degrees. So you have this, rotate, recycle, rotate, recycle. So during this part is when photography is taken. During this part, there's no photography. The camera keeps going around to 240 degrees, and the film is transmitted to the reentry vehicles. And
We have a
I
few.
hope you understand that, because unless you see it and explain it a few times, it's a tough concept. Okay,
We have
so
a-
then it goes to
We have a few questions, Phil.
yes.
Anne asks, how did you keep galactic gamma from fogging the film? And the perigee suggests you had to reboost.
What do you mean by reboost?
I
I don't. We had no fogging or anything. We had no electrical discharges which generate tarantulas, spots on the film. We had nothing there. We're in space. We're in a deep vacuum. So I don't quite understand the question. I'll get back to it.
Okay, there's two more quick questions.
Yeah.
David asks, was there a shutter on the camera or did it act with a moving slit above the film?
Very good question. We had in the platen, which was a volume approximately that large, there was 10 pounds of stuff in a 5-pound bag. We had a shutter. We had a focus mechanism. We had special kind of motors. It was packed. The shutter, yes, for every frame, there was a cam-driven shutter, and it was a set of 2 beryllium blades that were very stiff, very thin, and for each exposure, they went like this: exposure, exposure, and the amount of exposure depended upon V over H, what the altitude was, where they were, and how fast the film was moving. And then there was the focus mechanisms, which we rarely ever used. We were almost always in focus. The very first launch, for every launch, and there were 19 of them, the first mission took lots of pictures in the United States. In the Midwest, they were big circles, like 10 feet in diameter, of tri-bar targets, where we knew with black and white lines, we knew exactly how wide they were, the separation, and how straight they were. And those pictures were analyzed when the first reentry vehicle came back, and they told us if any of those lines were not straight, or what their resolution was in inches, we could adjust it using a focus mechanism.
I think
Okay.
Larry had the same question. And just you were at about 8:18.
What's that?
We're at about 8:18 for time.
Oh, so how much time do I have left?
We can go another 15, 20 minutes, right, Ben?
Oh, okay. I just realized 8:18 is Eastern time. I'm on Pacific time. Okay,
Sorry.
so the film went through and filled up the first reentry vehicle. It went through rollers and through the core. By the way, the core of the reentry vehicles and the core of the supply reels, especially the supply reels, had lots of electronics. The core was very complicated. We designed them, and Kodak, we shipped them to Kodak. They wrapped the film around it very, very well, perfectly aligned. The cores had bearings, motors, encoders. And so here it went through this core, through a roller, and on to the first vehicle. You can see an arm here. Let me see if I can point it out. Okay, this arm was a potentiometer that was with a roller that contacted the layer of film, and as it grew, it told us how much film was left, how much was there going to be left to be transmitted. Once it was transmitted, the film was then cinched backwards into the second reentry vehicle so that it was pinched in place. And then the film here was cut with a guillotine cutter. And the film was cut, and then And then this reentry vehicle was released. It went through the atmosphere and the heat shield protected it. And at 50,000 feet, I'll show you then what happens next. Okay? All right. Then the whole system that we built in Connecticut, the cameras, the film path, a huge amount of material was sent to Sunnyvale, California. There were 5 contractors on this program. Lockheed at that time was not Lockheed Martin, it was just Lockheed. They designed the vehicle, they integrated the camera system, which was in a box that had to be temperature, humidity controlled. It was so large, the only plane that could get it from Connecticut, from Bradley Air Force, from Hartford to California was the C-5A. Then there was the film that Kodak supplied. The reentry system was supplied by McDonnell Douglas. They supplied all of the reentry vehicles. So that's 1, 2, 3, 4. I think that's about it. Okay, so now at 50,000 feet, there were 5 KC-130s. You can see the trapeze underneath it, scouring the airspace where it was predicted that our reentry vehicle would be at. At 50,000 feet, a parachute was released. The trapeze caught the parachute in midair, or one of them caught the parachute, and then hauled it inside the aircraft, and then brought it to Hickam Air Force Base, and then sent back to the East Coast. One parachute did not deploy, the vehicle fell into the RV fell into the Pacific Ocean, 16,400 feet deep. The CIA thought it was a very important mission because they had good weather and extremely good photography, and they wanted to retrieve it. And they also did not want the Russians to retrieve it because the Russians had ships that manned the ocean near Vandenberg to monitor launches, and they had ships in the recovery area. They did not want the Russians to recover this top secret film container. So they hired the Navy, who owns this device called a Trieste, which contains a bathysphere piloted by 3 men, 3 Navy officers. And they hired Perkin-Armour, my company, to design a huge claw in order to go down. It took them months to find, well, they knew roughly where it was, but it took a long time. They had to practice off of San Diego. They had rough weather, but eventually they did catch it. And here is the supply. Here's the reentry that was on the floor, 16,000 feet deep, and the Trieste was able to grab it, haul it up. Unfortunately, by the time it got up, there was so much damage to it that all the film came off, and there was no results available. They were hoping that the central portion, that the edges of the film would have swollen due to the water and protect the central 2-3 inches, and they could have gotten some pictures, but that did not happen. But everybody was happy they tried it anyway. The very last mission, unfortunately, exactly 3 months after the Challenger exploded in Florida, the last Hexagon exploded 800 feet above the pad at Vandenberg Air Force Base. And I wasn't there, but when I found out about it, I cried. It was really very emotional. Okay, so here's another picture. Here's a submarine base in Russia. Here is a picture of a Russian aircraft carrier Okay, this is a missile site in the Soviet Union. You can see the gantries, the launch pad, and with 3D, we could measure the height of the missiles. Ken, this is not a great picture, but I can't show you anything better. Okay, with the satellite, we could orbit the Earth, and within a couple of days, we could see and count the number of airplanes at this particular Kubinka airfield in Russia. Unlike airplane sorties during other wars, where they left England or wherever, took pictures of an aircraft field, came back. Here with the Hexagon satellite, within 2 days, we could photograph all the airfields in the Soviet Union and count all of their planes in almost one shot. Huge advantage. Okay, this is a picture of the Eiffel Tower in Paris. I have lots of pictures of things in the United States and Europe and England, but I just thought I'd show you this one. And here's a picture. As I told you, we did a study, a couple of the fellows and I, whether the shuttle could fit in, the hexagon could fit into the shuttle. The hexagon was just an inch or two short of 60 feet long, and the shuttle was an inch or two to accept that. So it could have flown, but unfortunately it never did. So that's basically the end of my presentation. I'd be happy to take any questions. Did I make it in time?
Yes, thank you. Thank you. That was amazing, Phil. If people want to unmute, you can give Phil a round of applause.
Thank you.
There's a couple more questions.
Yeah, I'll go to the slide if necessary. Go ahead.
Okay. Could only monos be taken if only one camera was active?
Yes, we took mostly stereo, but we could take mono pictures with each camera as we wanted to. Yes.
I think that's all the questions in chat. If people would like to ask questions, you can switch to gallery view. And
okay. If you notice here, I didn't mention the rotational axis and the optical axis ideally should be coincident, because otherwise the film axis would be precessing around the optical axis. We were able to get them concentric to within 2 10,000ths of an inch by controlling the machining tolerances on all the hardware and specifying. We bought the highest class angular contact bearings possible. We tested them all. We threw out the ones that had too much run out or eccentricity. We phased them in such a way to minimize any kind of run out. And I didn't mention that before, but that was important.
Bert has a question. What kind of communication did the base have with the satellite?
It was all computer based, electronic based, and I don't have any other answer to that. I wasn't involved in that kind of thing. I was just involved in designing the cameras, and I assisted in designing many other parts. But I have a fellow in the Air Force who contacted me a while back. He was in the control building. It was called the Sunnyvale, Lockheed at Sunnyvale integrated the whole vehicle. Well, a mile away, there was a building called the Blue Cube, owned by the Air Force. And it was ultra secret place. And they are the ones who controlled and gave commands as to what pictures to take and when and where. I was in there, but I really don't know how they did it.
Somebody's keyboard is not on mute.
Sorry.
There's one more question, and then we will get to Dave has his hand up. Larry asks, did iTech participate in your program, or did they only work on other satellites?
Very good question also. iTech had made other reconnaissance satellites, and they had come up with a concept that the CIA did not like. And they had arguments with the CIA. And the CIA came to us in 1965, and they told us, here are the requirements. We would like you to propose on how to do this. And iTech was very, very angry, and they had to send us their models, the physical model of how they did the camera, which was totally different from ours. And we spent a year at about $1 million a month to come up with the concept that I've just shown you. And in May of 1966, there were only 15 or 20 of us on the job. I was very lucky. I was on the beginning. And one other guy and I were the mechanical engineers. We designed all of the proposal, cameras, everything. And we then had a meeting in July with the CIA and their representative, and their representative was the President's Advisory Committee, who was chairman was Edwin Land, the inventor of the Polaroid land camera. And he was a very, very sharp guy. I sat next to him during the presentation. We made our presentation, and when we took him down to see the twister and the looper, he was blown away. And so they were very happy. And on October 10th, 1966, we got a wire, we got the job. And it was worth 1.5 times what the company in total was worth. The company was worth about $50 million. This program was worth more. Incredible. And that made us, eventually, we became $1 billion company, PerkinElmer did. Yep. Since I retired about 20 years ago, it was sold off to 6 other companies, which, and so the heritage of PerkinElmer is gone. It's really a shame. We had fantastic products. I was involved mostly in classified cameras and telescopes, which I basically can't talk about, but they were based in space and telescopes based in the Middle East and other places. And it was great, great work. It was, the CIA was tough, but they were very good managers, good engineers, and they did give us a hard time, but we worked for the Science and Technology Division of the CIA, not the quote unquote bad part.
Okay, Dave had his hand up. Dave, do you want to ask your question?
Yes, thank you. Hello, Phil. I really enjoyed your talk. It's really I can't imagine the complexity of that mechanical film device. But one question about the a cutaway image you had of the optical system. I'm assuming that the flat diagonal mirror was a complete mirror. It looked like there were 2 separate elements to, you were there.
I will describe it in detail. Oh, is that what you're talking about, this one? The camera? Oh, wait, let me
camera,
go to
the flat mirror that feeds the image into the telescope is,
okay.
Yes,
okay.
Here I see the folding mirror. There's 2 elements to it, but I assume it's continuous, is a continuous circle.
Each mirror was made of 2 half-inch thick fused silica sheets bonded thermally to a core, which was 3 inches thick. The core before being fused to the back faceplate, had 80% of its weight drilled out from the back. So the back was full of holes, okay? And there were 3 holes in which we tied flexures to hold the mirror. And the flexures should always be held at the center or CG plane of the mirror. So
But
that
excuse
it,
me, the question I had was that it looks like there's 2 mirrors, but indeed it's a single mirror. I just wanted to confirm that in 3 dimensions.
this is one mirror.
No, to the left. Go to the left.
And this
Sure.
is one mirror.
It's one
Yeah.
single mirror. That's right. Okay.
It's 4 inches thick, 3 inches of core, 1/2 inch front and back face plates, all drilled out with a large hole in the middle to fit in the lenses, which were held by an aluminum housing.
That's right.
Does that answer you?
Yes, that answers it. Thank you.
Oh, you're welcome. I forgot also to mention the focal plane with 120 feet, I'm sorry, the film path with all of the rollers had to have lots of mechanisms because we had to keep the film from sliding off of the rollers, curling up. We had edge sensors and all kinds of flexures and alignment devices. So that's why it was so complicated. We had to design so many things. Okay, yeah.
We've got a bunch of questions. How are we doing for time, Ben?
I would think we could try to get through the questions, but we
Okay.
do not have a lot of time left to socialize at the end. But I think these are great questions, so let's get through them.
Reich had a couple of questions. Reich, do you want to ask them directly?
You're saying Rick?
Reich.
Yeah, it's right. Hi, Phil.
Hi,
Great
Rick.
having
Good.
breakfast with you the other
Nice
day.
to see you again.
Yes, indeed. Was the KH-9 able to change orbital?
What?
Yo, was the satellite able to change orbital height up or down, or was it more or less in a fixed height orbit for each satellite?
It was kind of in a fixed orbit. It did not have the capability of moving all over the place.
Can I interject, Dana? Dana?
Yeah, Reich, could he just finish
I'm
his
going to answer the
question?
question, Dana.
Go ahead.
I'd like to answer the question, Dana. We good?
Yeah,
Okay, I'm the colleague that Phil mentioned earlier. I was a captain for 4 years at the Blue Cube. And yes, first of all, we'd be in communication about every 90 minutes through a tracking station. We would prepare commands and the CIA would come over and tell us what targets they wanted. We would intersperse those and put them in a computer that would generate information to go to one of the 6 tracking stations. And when the satellite would come over, we'd be in verbal contact with the tracking station. It would only be visible for about a minute to 2 minutes if we were lucky, as it was very, very low, about 100 miles up. And when the satellite flew over, we would transmit up the commands to be done in the next couple orbits. And it would read down tracking information and telemetry to the manufacturers that made the components of that. They could look for any anomalies, and we had commands we could send up during that minute or so to change something on the fly, or we would have to work on it with the satellite that Phil showed earlier. It was a development satellite, but we could go in on anomalies and the engineers could replicate perhaps what the problem was. And yes, about every 3 days, we would have to do an orbit adjust because the atmosphere is still up there, and it would bring the satellite down. We couldn't rotate it or do anything other than when we were going to eject one of the buckets, one of the RVs, or at the end of the mission when we were going to burn in the whole satellite. Thank you.
Thank you, Rick. That was good explanation.
Yeah.
This is the guy who should know. Thank you.
thank you. I'm going to take the rest of the questions down in order. Sid had a question. How many how many at PE worked on getting the first unit ready?
Approximately 1,000 people worked on it. All departments, electrical systems, mechanical, we had drafting boards, we had reliability, quality control, purchasing, every skill, we had people. So we had approximately 1,000 people who had to be cleared.
And Sid also asked, when did the Soviets find out that you were photographing their installations?
I can't answer that. I don't know. I know they knew about it, but I don't know when they actually found out.
And Ben said, when does the Hollywood blockbuster start filming? Because it would make a great movie.
Yeah, several of us have thought so too, but I don't know. The explosion of the last one happened about 36 years ago, 22 and 14, 32, 36 years ago last month. So it's been a long time.
All right, we have a little bit of time left. Vlad says he has a story and a question, and there's some more questions after that.
Okay.
So do we have you have a couple of minutes for my story?
Yeah.
Okay. We came to United States. It was 1991. I came to United States from Latvia. If Phil, you probably know the country. And the first person who visited us was someone from FBI. Why is that? Because I worked for a big plant that was like 9/10 military production. And he visited us. He spoke very good Russian, and he opened a map, a very detailed map of the entire plant. The plant employed about 20,000 people and had like 5 blocks in territory. Maybe even more. So from that map, I figured out even details that I did not know when I worked on that plant.
Wow.
Do you think this map was taken by Hexagon?
Well, Hexagon ended in 1986, so I don't know. I have pictures that I personally requested when I was on the job of my home in Connecticut. And so that was back in 1982. And I have pictures of my home now in San Diego. I just asked for them and they did me a favor and got them, but I don't know if
Have you, I'm sorry, have you heard the name VEF in Riga, Latvia? VEF is the name of the plant.
How do you spell that?
VEF, VEF.
No, I have not heard of it.
No. Okay.
Anne, did you want to ask your question? And then Ricky, did you want to add something after that?
Well, I just wanted to give Phil a round of applause for the book that he wrote. If you're interested in all of the details that he covered, an excellent job cover to cover. So thank you, Phil, for writing the book. I learned quite a bit because we were very compartmented in this program. You were cleared to do what you did and you weren't able to. I didn't even see the vehicle. It was made at Lockheed right across the street and it was that tight. But Phil did an excellent job with unclassified information. It's called Meeting the Challenge. There you go. And it's available.
Thank you, Rick.
Yeah, good job.
Yeah, if I could just interject here regarding books, that was actually Phil's second book. His first book dealt with his Holocaust episode and all that was going on there. So that's also available if you want to look that one up.
What's the title of the first book, Phil?
They Are Still Alive. It's available as is Meeting the Challenge on Amazon, both under my name. They Are Still Alive. As yeah, I'm a Holocaust survivor. I wrote it when I retired. I spent 6, 7, 8, 9, 10 years old, and I remember everything. I went through a lot of bad stuff. So yeah, that's that book. And the other one is Meeting the Challenge. So thank you. Yeah,
Thank you.
I unfortunately I still suffer from PTSD from the war, and I got in counseling, but it's hard. But I'm an old guy now.
Oh, thank you. Ben has posted links to Phil's title in the chat through Amazon. So you can click on that and or save that link and buy Phil's books. Thank you, Ben. Let's see. There's one more thing. Anne, did you want to ask a question?
Yes, I wanted to ask if the optical paths that you show here are in vacuum, or is that in a pressurized space?
Well, I'm just showing a picture of the camera itself. An optical engineer expert is the one who came up with the optical design, meaning the focal length, the distances from vertex to vertex, the curvature of the various lenses, all of the optical elements, and then I just put metal to wrap it up and hold it in the proper place, the proper way, and to prevent it from moving, etc. So what you're seeing on the screen now, it's either in air or in a vacuum. We tested all of these in a thermal vacuum chamber. We had one chamber just for the optical bar. It was a little larger than this thermal vacuum. And then the whole thing was tested in a larger chamber. And eventually the whole system at PerkinElmer was tested in the world's largest spherical thermal vacuum at the time. It was a huge, huge chamber. We had film and closed the doors, and we ran lots and lots of tests. Lockheed did the same thing at Lockheed in a different kind of chamber, but we also tested everything on vibration, vibration isolator, vibration machines, basically, and in acoustic chambers. We tested them in thermal chambers, etc. Every kind of test you can imagine. So.
Thank you. I think we're coming to the end of the questions. If people have additional questions for you, Phil, what would be the best way for them to reach you?
Okay, that would be work. I want to thank everybody for listening. The questions were really good. And I'll give you my email. If you have any questions, just email me. It's Phil, P-H-I-L, .Pressel, P like Peter, R-E-S-S-E-L, Phil.Pressel @gmail.com.
Great.
And that's my email. Just write to me. If you look at the YouTube in a few weeks, if you can identify the slide number, if it relates to your question, that would help. I can send you, email you, or if you want to include your telephone number, I'll be happy to answer you. The only thing is today is Sunday. This coming Wednesday, my wife and I are flying to the East Coast to see some relatives we haven't seen in 3 years because of COVID. And then we're going to go sightseeing a little bit in North Carolina, Virginia. As I mentioned, we're going to go to Rochester, New York, where I'm giving the same talk to the alumni at Kodak of the Hexagon program. That should be fun too. That one will be in person at a luncheon. So I won't be back home until May 21st. So I'm away 2.5 weeks. But after I come back, I'll be happy to answer. So
Great.
thank you very much for everybody. Good audience.
Thank you. Everybody, one more round of applause.
You bet. Boy.
Great job, Phil. Thank you.
Thank you very much.
Phil, wonderful to see you again.
Yeah. Same here, Rick and John. John, when I wrote the article for your PHSNE Journal, John was tough. He made me go through lots of stuff that I hadn't planned on. And he's a perfectionist. He wanted everything detailed. And I'm glad I did it. It turned out okay.
Me too, Phil. I think it's one of the best articles we've ever published. And anyone who becomes a member of PHSNE gets the free journal. So we encourage people. Thank you for that lead-in, Phil.
Okay. Maybe someday I can write another one about one of the other classified programs because they were pretty interesting too.
Sure.
But I can't. Right now I can't do that.
Keep going.
Okay, thank you.
Going.
Thank you. Ben, are we about ready to close the meeting? Do we have time for people just to greet one another, or?
Yeah,
would you
let's
like to do?
it's 8:52 right now Eastern. So let's why don't we take until like 9 o'clock or less for people to maybe say hello or good night.
Yeah. Phil, this is Sid Chatterjee again. Could you just give a shout out to some of the optical engineers who worked on this project at Perkin-Elmer?
Oh, you
Yeah.
want that
Was,
name?
yeah, was Justin Kraser on the project or not him?
No, I knew most people on it. The first optical engineer was a man named Lloyd McCarthy.
Okay.
And then he was succeeded by Raul Casas.
And this is up at Worcester Heights then?
Yes.
Yeah.
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 It was at Worcester Heights.
Yeah.
And then after him came Mac. I forgot his last name. Mac. I can't remember his last name, but those were the main ones. I also worked with Kevin Thompson. I don't know if you knew him. Genius. And
Yeah.
unfortunately he passed away
Yeah.
years ago, but
Mhm.
we had some really talented people.
Yeah, yeah.
And then we had like one of our upper managers was Dick Babish. He invented,
Yes.
oh, you know Dick, he invented Cinerama.
Yeah.
And then Rod Scott.
Well,
Anyway,
no.
there were a lot of good people.
Yeah.
And our president of the company at the time was Chester Nimitz Jr., the son
Yeah.
of the famous admiral.
Yeah.
He was an admiral himself in the submarines.
Yeah.
So. Okay.
Okay, great.
Ricky, the Zoom will be posted on the PHSNE YouTube channel. So if you search for the YouTube, you search for PHSNE on YouTube, you should find all the recordings, and Phil should be at the top. because it's the most recent, right, Ben?
Yeah, you can get that off our website, that information.
That's right. It will be there in about 7 days or less, 7 to 10 days.
Yeah, PHSNE.org.
And I just also gave a link in the chat if anyone wants to click through. And
Yeah.
make sure you subscribe, log into YouTube and subscribe to the channel for all the upload updates.
Well, I've been in touch with Rick, and he contacted me some months ago, and he gives other lectures about many, many topics. But since he was on Hexagon in the control of the system for the Air Force, we're going to try to do a joint lecture, each about half, where he talks about the control aspect of it, and I would talk about kind of the details. I think we each have to shorten our talks, but we're hoping to do this somehow, someday, with some group.
Well, keep us posted. Maybe we
Yeah.
can arrange that for you.
That would
It'd
be
be
nice.
great.
Okay, we'll see.
Yeah, that would be wonderful. Let's see. And I had a question. How many women were working on the project?
Very few. That's one of the things I
Immense.
regret terribly. We had one lady, chemical engineer, one lady, optical kind of engineer, a lot of secretaries, but in responsible technical areas, very few. And I feel very bad about that. It just, I'm so glad things are different today.
Yeah.
Good
Yeah,
question.
We had one woman officer that worked on our program, and I've kind of kept up, and she got out of the service now, but she was a full colonel when she got out.
Wow.
Right.
Well, I know one
Wow.
woman at the NRO. I dealt a lot personally with the CIA and the NRO. There was one lady at a reasonably high position at the NRO. But not many.
Mhm.
So
If Phil, if I could just ask now, they don't do film anymore. It's all digital, the satellites now, correct?
that's correct. And that brings up a good point. Film happens to take much better resolution than a zillion pixels, period. And so film took better pictures, but now the digital world is catching up, and they're almost as good as film. I would say some of the cameras are probably as good. Good question, but yeah, they don't use film anymore. It's all digital.
And they can get the results back and read a lot faster, I would imagine, right?
Oh yeah, here we took pictures of the Middle East, for example. Like in 1973, we were operational. We gave lots of photographic information to Israel during the Yom Kippur War. And today they would get that instantly through electronic transmission. We didn't have that. It was all film. You had to wait till the vehicle came back. And sometimes they waited a long time because if there was no critical information that had to be given to or analyzed right away, then they might have to wait weeks or more. So digital has its major advantages.
Yeah.
You can get the information very, very quickly.
And you can also count on most other countries also taking real-time video from space. I mean, this is old hat by now, but they're all, many of our programs are classified beyond what I or Phil have access to. So rest assured that most people have it. The Russians have it. That was part of the trust and verify, was open the kimono on both ends of it so they could see what we were doing in the treaty and they could see vice versa. So it's out of the box now. In fact, commercially, there are companies now that you'll see for Ukraine that pictures are available And in some cases, it's just better and faster for the government to purchase those pictures rather than having resources dedicated to that. Google Images, for example, it's not real time now, but who knows what it's going to get to.
Right, that reminds me, back in 2016, I was on CNN with the Director of National Intelligence, James Clapper, and the whole hour program was about Hexagon. And they did ask me about how does this compare to Google Earth? And at that time, I kind of feel bad. I joked around them, oh, this is so much better than Google Earth. Maybe not anymore now, but at that time, it was, you know, Google Earth had like meters or 30 meters resolution. Now we have better than 30 inches or much better. So,
Phil, were you part of the proceedings when the Hexagon was exhibited at the Udvar Hazy Center?
I was there for that. Yeah, that was September 17, 2011. It was a celebration of the 50th anniversary of the creation of the NRO when they admitted that they existed. And it was the release, the declassification of Hexagon, period. And it was at the Udvar Hazy Museum, yes. Were you there too?
Well, I was a curator there at the time, yes. And since then, I believe that it's going to be on display in the new Cold War gallery. But I've been retired long enough so that I'm not sure about it. I certainly hope it will be.
Well,
have you been in contact with Jim David?
you mean from the Smithsonian?
Yes, Jim David.
Yeah, I know him. I've lectured on this topic at the Smithsonian for
Right.
him, yes. And right after the declassification day, the following week, the Hexagon, the real thing, and it was a model, which was eventually upgraded that it could have flown. It went to the NRO on exhibit for a week, and then it was shipped to the Wright-Patterson Air Force Base at the Air Force Museum in Dayton, Ohio, which is where it is now. I've lectured there twice, but I think they expect to keep it forever. I did not know that it might have. We were all hoping it would be at the Smithsonian or the Udvar Hazy.
Well, I looked at the website just now, and it sounds like it's going to be going into the Cold War gallery. The museum right now is closed because of a complete renovation. And I certainly hope it'll be part of it.
I hope so too. It'd be great. Its name's changed now from Udvar Hazy to the space. Isn't it called the Space Museum or something like that?
No, it's two different. Udvar Hazy is the support museum at Dulles Airport.
Right.
The Air and Space Museum, it's part of the Air and Space Museum, and that's on the National Mall.
Okay, yeah, I've been to both. Right.
And that's where I think they're talking about it's going to be on display there is going to be a new Cold War gallery, but I'll try to double check on that.
Okay, if you find out, let me know, please.
Sure,
yeah, I know.
will.
Jim is based at the Smithsonian. Yeah.
I have your website. I have your email. Sure.
Okay.
I could just interject, you know, I have a daughter who lives in the Washington, D.C. area, and she took me to the Spy Museum. And sure enough, they had one of the recovery vehicles on display there. So if you're ever in the Washington, D.C. area and
No, Kitty, you're not going out.
if you want to see one of those
No.
capsules that was captured by the plane and with the film in it, they have one on display at the Spy Museum, International Spy Museum.
Yeah, I was interviewed there, and the advantage to that is you can actually see film at the Spy Museum, which you, at the whole vehicle, you can't see any film, it's all hidden. But at the Spy Museum, you can see the film, it's on a take-up reel.
I was trying to convince some people that were looking at the display that I know the guy who designed all that stuff, but You didn't seem too interested. Sorry.
Phil, I don't know if it will be possible, but if people have questions, do you share the slideshow that you presented today?
No, I have not. I've shared, individual photographs or drawings or pictures,
Okay.
but I haven't shared the whole thing.
Well,
So,
this is an incredible presentation, and I want to thank you so much.
well,
We
now-
are really looking forward to putting this on YouTube and sharing it, with
Yeah, now it
with
will be
others.
shared automatically on YouTube.
Right.
I didn't know that until just recently. Ben told me that.
Yeah.
So,
All right. So
all right, thank you very much. Appreciate it.
thank you.
Thank you,
And,
Phil.
and
Bye.
bye. Thank you.
Yeah, I'm
Good
gonna
night,
sign
everyone.
off
Great
now.
job, Phil.
Okay, thank you. Bye-bye.